Welcome to our next video while we study linear functions. This one is going to be focused on determining intercepts. We're also going to look a little bit at transformations of lines. First, we're going to identify what intercepts are, and then we will look at finding those intercepts from the graphs and from equations. So first, we need to ask ourselves, what are intercepts? And specifically, if I draw a little grid here, don't worry about counting it, and I draw some line. An intercept is the intersection with an axis. Remember that a graph is made up of two what are called axes. There is the x-axis and the y-axis. They meet in the middle at the origin, which has the coordinates 0, 0. That's the beginning for everything. This breaks this grid up into four what are called quadrants. You may remember studying these earlier and calling them Roman numeral 1, 2, 3, and 4, starting in the top right and moving counterclockwise. So that means going top right, top left, bottom right. Everything on the axes, when you go to the x-axis right, is positive. Everything to the left of the origin is negative. Everything above the origin is positive. Below the origin is negative, which means everything in quadrant 1 is a positive x and a positive y. Quadrant 2, negative x, positive y. 3, negative and negative. 4, positive x, negative y. That never changes. That is a constant for everything. Now, intercepts are simply where the line or any graph touches an axis. It's the ordered pair of the point where it hits the x and the point where it hits the y. Now, curved graphs might hit more than once. Every graph crosses an axis. Any graph that's open that has an arrow on an end hits at least one axis somewhere. Graphs that close, like circles or ovals, it is possible to draw them without them ever having an intercept. But things like lines or anything that is open-ended always hits at least one of the axes. Now, lines are special. Lines normally hit each axis once. They will never hit twice or more than that. But special cases will only hit one axis. Otherwise, all lines hit both axes once. Think about it. The equation had an x and a y. If it has an x and a y, then it has to hit the x and the y. However many variables it has, that's how many times it touches an axis. So first, let's look at how to find this from the graph. When I look at the graph, all I'm going to do is actually just mark dots. Now I'm going to write down here on the bottom, I'm going to write x-intercept and y-intercept. And I'm going to look at the x-intercept first. Now, x-intercepts always have the same pattern. As an ordered pair, it's always a number, comma, 0. Because whenever you are on the axis, you have a 0 term, or a 0 coordinate. That just means it's half of an ordered pair. Y-intercepts are always 0, comma, our number. Now let's look at the x. Our x is right here. Now there's a problem. Notice that we talked in a previous video about lattice points. Remember that lattice points are your grid points. This is where your graph, where the grid lines actually intersect. If you can't hit a lattice point, then on a graph you can't read it. That x-intercept, that orange dot, cannot be read. It looks like, you might say to yourself, well, that's at a half. Well, I'm going to tell you, having done the math on it, it's actually at 2/5. Think about that. You can't read a graph at 2/5 unless it's drawn special for it. So this is a case where we're not going to be able to mark the x-intercept. It is there. You cannot say there isn't one. I'm going to tell you that I just happen to know that in this case it's at 2/5 because I know the equation for this. And I will always make certain to give you ones that you can read if I'm asking you to find it on a graph. But don't estimate. Don't do that. Don't try to be close. Either you can say what it is or you can't. And if you can't, you're going to have to say, can't tell. Don't say it doesn't exist. It does exist. We'll look at one where it doesn't. Now, if we look at the y-intercept, and I'm going to switch to green on this, that is right there. That is at a nice, neat point. And when I read that, that went up the y-axis to +1. So my y-intercept is 0, 1. Now let's look at this other one. And again, I'm going to write x-intercept, y-intercept. I always like to put some titles down. And I know that my x-intercept is something 0, and my y-intercept is 0 something. So let's look at our x-intercept first. So again, I'm going to go to orange. Notice this blue line does cross the x-axis right there at -1. But now we have a problem for the y-intercept. If you look at this line, it doesn't touch the y-axis at all, which means I can't make an ordered pair. So this is a case where we say that it does not exist. You could say no solution, no answer, doesn't have one. You could put a lot of different ways to say this, but it doesn't exist. This vertical line does not touch the x or the y axis at all. You've got to look out for that, and I'll show you in the equations how to tell. But first, let's look at a basic equation. We're going to look at 2, and then we'll talk about the special case. If I look at this, so when we look at this, let's look at y equals -1/4 x plus 1. Let me clean up my 4 a little bit. Now I want to know what the x and the y intercepts are. Now there's a very short way of dealing with this. So it's simple. I'm going to actually draw a little vertical line here this time. It's all about the ordered pairs. Remember, an x-intercept has an ordered pair that is something, comma 0, while a y-intercept has an ordered pair that is 0, comma something. Notice this something is your y value, and this 0 is your x value, and that's the key. So what I'm going to do is I'm going to replace the variable with a 0 for the one I don't need to find. I want to keep the variable. When I'm looking for an x-intercept, I need to keep the x. So I'm going to write, instead of as y, I'm going to put 0 equals -1/4 x plus 1. Now all I have to do is equation solving. Solve for x. So I'm going to subtract 1 equals -1/4 x. I'm going to multiply by 4. I am doing the longer method here. So -4 equals -1x. Divide by -1. So that's going to give me 4 equals x. That means that my x-intercept is 4, 0. For the y-intercept, I'm going to replace the x. So I'm going to plug a 0 in. Don't get these backwards, that does make a big difference. Well, that's neatly going to cancel out completely, so I get y, make my y a bit better, equals 1. So that means it's 0, 1. Remember, when we dealt with graphing, if it was y equals, then this number right here is automatically the y-intercept. That's a shortcut. It doesn't help you with the x-intercept. This number is not the x-intercept. Now, let's say that we have this in a different form. Let's say it's not in y equals, and I want to figure out the two parts fairly easily. Let's say that I have 3x plus y equals -6. So I'm going to say x-intercept, y-intercept. So I'm going to first, for x-intercept, I'm going to replace the y. 3x plus 0 equals -6. Well, that whole term gets to cancel. So I'm left with 3x equals -6. Divide by the 3. So x equals -2. So -2, 0 is my x-intercept. Now for the y-intercept, I replace the x. So 3 times 0 plus y equals -6. Cancel it out. Y equals -6. So that means 0, -6 is my y-intercept. Now remember that we said that there are special cases, and we talked about this a little bit earlier. If you have just an x, if you have x equals 3, in this case, that is the x-intercept, 3, 0. But there is no y-intercept because this is your vertical line. If I have y equals 3, then my y-intercept is 0, 3, but there is no x-intercept because there is no x value. You have to think about what letters are there. If you see an x and a y, then you have an x-intercept and a y-intercept. If you just see an x, then you have an x-intercept but no y. If you see a y only, then you have a y-intercept but no x. It depends on the variables. Now the last thing we're going to talk about are transformations. You should have studied these in geometry, but we do use them a little bit in algebra when we get to shapes. With lines, there's only two transformations that we're going to care about. Only two for lines. We're going to ignore ones like dilation and our rotations. Dilation, remember, makes graphs get bigger and smaller, but equally. Rotations spin them around. We're not going to worry about rotations at this point. There is a case where it works, but for right now we're going to focus on two. The two that we're going to look at are a translation, which we're going to call a slide. translations for lines, for a line, move up or down. We're going to ignore left and right. With a line, if you move it up and down, points have also moved left and right at the same time. So it gives the appearance of that. We're also going to deal with a reflection. Reflection, remember, is a 180-degree rotation, but it's specific around a special line. It's around something called y equals x. This is a very important line. It's called the identity line. It is the basis for everything that is a reflection, called an inverse. And when we're talking about reflections, we're talking around and over an axis. If you flip it around an axis, that's called a reflection. Now we're going to look at two examples here. Now I've drawn a red line and a blue line. Now our goal is to look at what is happening to make the graph go from the red to the blue. So we're looking at from red to blue. Because if you go from blue to red, that changes it. It's going to be different. Now if you look at this red line, the first thing to look for is to look to see if you slid it at all. The easiest way to do that is start with the y-intercept. That is the most important point to look at. So I'm going to look at the y-intercept. So on the red line, it's down here at -2. The blue line is up here at 1. So it did move. It went up from the red to the blue, and we want to know how far up. It went up 1, 2, 3 spaces. So the first thing is it translated, or we're going to say slid 3 units up. Now I'm using the word units because we don't have inches or centimeters or feet or miles. We don't have a measurement here, so we're just going to call them units. That's a general word. Now, I said it slid up 5 units. Now we want to check to see if it reflected. So I want to know, did the slope change? So if I start at this dot and I find the slope. So here's another point. My slope here is 1 to 1. So my rise is 1, my run is 1. So my slope is a positive 1, because again, it's going positive. If I look at the blue, here's another dot. That's also 1 to 1. The minute I see that the slopes are the same, then I know it couldn't reflect. The slopes are exactly the same. They have the same rise and run, and they have the same correlation. They're both positive. So that means this translation is the only transformation on this graph. Now let's look at the next one. I look for the y-intercept first. Notice the y-intercepts are exactly the same. That means there is no translation. So we first looked for our y-intercept, and then second, check the slope. So I'm going to check the slope now. So I'm going to do the red line first because that's the line I'm starting with. So I'll need to find, okay, there's another dot. Just like before, this is a 1 to 1 ratio. So my red slope is 1 over 1, so it's a positive 1. Now let's check the blue. And actually, I'll switch to a blue dot. So I go, let's say here. Again, notice I've got 1 and 1. So I've got 1 over 1 but it's a negative slope. Notice what happened to the slopes. They are opposites of each other. That's very important. That means that these are reflections. If I flipped one around, it would become the other. If I turned it 180 degrees, or sorry, 90 degrees, it would become the other one. So this is a reflection. And all we have to say is it went from a positive slope to a negative. If you notice, the slope is still the same. It's still a 1, it just switched signs. If you have the same exact number, but the sign changed, that means it just flipped around. It's just reflected, and we actually say it reflected over the y-axis. It's as if you grabbed the y-axis from the top and the bottom, and you spun it, and you looked at it from the back side. So you're looking through the front, you spin it, you're looking at the back, you now have a reflection. Think mirror image. The image is the same, it's just in reverse. So that means that this is simply a reflection. It is possible to have more than one transformation. You could translate and reflect. Now there's a key word to make note of, and we'll talk about it more in the future, is your first line is what's known as a parent graph, and the second line that it changed into is a child graph. All lines have that y equals x as their original, let me clear that up, have that y equals x as their original parent graph. That is the grandparent of all lines. But you can, any line that you're starting with, you can call a parent, and it turns into a child graph by transforming. In the future, we'll talk about rotation more as we change slope. We won't deal with dilation here, but dilation affects other shapes a lot more than it does lines. So remember, as you go through the practice, if you need to come back and watch this again, go for it and make good use of it, and I will see you in another video.